Hey everyone, welcome back to the channel. In this video, we're going to talk about thermodynamics and we're going to focus on processes and cycles. We're going to look at process diagrams, types of processes, as well as equilibrium and its use to analyze processes. But before we get started, if you like this channel, make sure to subscribe and like the video and come back for some more content on this channel. So we're going to start with a analysis of a process diagram and understand how to draw a process diagram. So a process diagram is written on a graph usually, and it's either written on a PV diagram or on a TV diagram. And as you can see here, we have a PV diagram with a process from 1 to 2 that goes from a high volume to a low volume where the pressure increases. Now, there are many different types of processes, and I want to highlight the different types of processes so that we can move forward in our study of thermodynamics. So one specific type of process is called an isoprocess, and an isoprocess is when a property remains constant within the process. So one of the properties that we look at is pressure, temperature, and volume usually. So these are called isoprocesses. So when you have an isothermal process, which you've probably heard of before, you would have that temperature remains constant. If you have an isobaric process, that would be that pressure is constant. And finally, an isochoric process is when volume is constant. And that one is probably the only one that is hard to remember. So isobaric you can remember because pressure is measured in bar. Isochoric, it's kind of hard to relate to volume, but hopefully you can remember that. Now, a cycle is drawn on a PV diagram as a system that returns to its initial state after a series of processes. So we might have 3 or 4 processes in a row, or 5 or 6, or however many processes. And the specificity of a cycle is that it returns back to its initial state. So an example of this would be if we take our process from 1 to 2, going from point 1 to point 2, and we call this path A. If we then go from 2 back to 1 through path B, we complete a cycle. Now, before we continue in our study of processes and cycles, what I want to do is define a few things that we need to define based on the analysis of introductory thermodynamics and some things that we use as assumptions to make our life easier when we do calculations. So a pure substance is one that is uniform and invariable in chemical composition. This is important for us because we're going to assume that most substances are pure substances. So when we have a mix of two things together, sometimes we can't call this a pure substance, but for example, water can be thought of as a pure substance because it's perfectly mixed essentially. Now, it can exist in more than one phase, meaning that water could exist as a liquid and a vapor at the same time, and that can still be considered a pure substance. In most cases, when we study thermodynamics and we study introductory thermodynamics, we also assume that air is usually considered a pure substance. So we consider air a pure substance, although it's a mix of nitrogen, oxygen, and other gases. Now, the next definition that we want to go over is the definition of equilibrium. And this is going to be very important for us to understand what equilibrium is and how we can use it to our advantage in our study of thermodynamics. And this equilibrium definition only really works when you have slow-moving processes. So equilibrium means that the values of all the system is the same for all its properties. So that means that if you have, for example, a container with a piston cylinder device, for example, with air inside it, we assume that, for example, at time is equal to 0 seconds, we assume that that air is essentially all at the same temperature. So all of the air, no matter where you look at it, will all be at 25 degrees Celsius. And that means we call this equilibrium. We call this state as equilibrium because everything is at 25 degrees. Now, after 100 seconds and we add some heat, we know that in real life we probably won't have equilibrium. We probably won't have the same temperature at the bottom than at the top of the container. However, in our analysis, to make our analysis easier, we assume that the air transports all the heat it perfectly around, and we have the same temperature all around. So there are different types of equilibrium that we're going to study and that we can use throughout our study of thermodynamics and throughout the learning of this subject. The first one is mechanical equilibrium. That means pressure stays constant. Thermal equilibrium means that temperature stays constant, and phase equilibrium means that the mass of the phases stays constant. So the mass of one phase or another would stay constant. And we're going to illustrate that in some way in the following diagram. So in the following diagram, for example, we could have that our system is in phase equilibrium before adding heat to it. So we could have a mixture of liquid and gas, of the same liquid and the same gas, within a container within a piston cylinder device, where we have, for example, 20% liquid and 80% gas, or we can also call that vapor sometimes. So if you have water in there, water can exist as a liquid and a gas. And that would mean that it would be in equilibrium. Now, if we start adding heat to the system, then our heat might change our phase equilibrium. So it might change that our phase will become 100% gas and 0% liquid. So that would happen, for example, when you boil some water in a pot, for example. That's a very similar situation to what we have above. Now, the next thing I want to talk about is quasi-equilibrium, and this is the assumption that we make when we solve problems in thermodynamics. What we are essentially assuming here is that all properties change slowly along a path line. So for example, if you're boiling water from 0 to 100 degrees, we can stop the boiling of the water at any point, record the properties, and we can assume the system will be in equilibrium. This is an assumption and is not actually the truth in real life, but it gets pretty close as long as the process is not too fast. So we're going to illustrate an example of this, of how we use this quasi-equilibrium analysis if we had a piston cylinder with, let's say, some blocks of 1 kilogram weight each. So if we assume that we start with a system that has air at pressure 1 and volume 1 and has these blocks added on top of the piston cylinder. So these blocks are going to somehow compress the air inside the tank by a certain amount based on the weight. And we have these 4 blocks, and what we can say is, let's record our pressure and volume at when we have these 4 blocks, and instead of removing the 4 blocks all at once, which would change the pressure and volume a lot, what about if we decided to remove the blocks one by one? If we remove the blocks one by one, the quasi-equilibrium analysis is well understood. Essentially, we're assuming that when we do a thermodynamic process, we're doing it slowly enough that we can analyze it and pause at every point on the path line. So if we were to draw a path line between 1 and 1b, which would be at the end of the blue block being taken away, then 1c would be the green block taken away, 1d would be the red block taken away, and finally when the black block is taken away, you would get to 2. Now in real life, we could take out these 4 blocks and we would get a similar path to what we just saw here. We would go from 1 to 2 along a similar path. Just to look at what's happening if we remove the 4 blocks all at once, or we remove them one by one, is eventually the piston moves from the start to the final position by moving up. So what we can say from this analysis is that quasi-equilibrium actually approximates most situations well in thermodynamics. So we can use this type of analysis when we have relatively slow movement of the piston and it's a controlled movement of the piston. And this happens in most situations in thermodynamics. Now, in some cases, we have non-equilibrium assumptions that we have to make. And these non-equilibrium assumptions are made when pressure is not uniform and the piston is moving too fast. We of course need to be able to define what too fast and too slow means, but we can do that at a later stage in our video series. So the next thing I want to talk about is steady flow processes and transient processes. And if you've been watching some of my previous videos, you might know already what a steady flow process and a transient process means, but I want to look at those two as a function of processes and looking at what happens in the process of that. So steady flow process means there's no change with time. So that means that anytime you look at a process and you look at it over time, there's going to be no change. And an example of this is a flow through a pipe. When we have a flow through a pipe, we can have a control volume analysis with our surroundings and our control volume, which is in green, and we have a mass flow rate in and mass flow rate out. Whenever we have that, we can see that anytime we look at the system, whether it be at the start or at the end or in the middle, our mass of the control volume is going to be constant. We're constantly going to have the same amount of mass in the system. And our energy of our control volume is also going to be constant. Now, if we look at something else and we look at a transient process like filling up a tub, we now have a different type of analysis. We start with a low level of water, or maybe from empty, and we're increasing the level of water with time. So we have a start with a control volume that is small and that is essentially expanding. So what happens to the mass in the system? Well, the mass is actually increasing. So our mass in our control volume is not constant anymore when we have a transient process. We have mass in and no mass out. We don't actually have a mass out until we drain the tub, for example. But right now, it means that the mass of the control volume increases, which also means that the energy of the control volume increases because there's energy associated with the amount of mass in a system. But we'll look at that in some future video. Now, another example of a transient process, just to give you an idea, is if you were to, for example, leave a hot tea to cool inside a room. So let's say I bring a hot tea in a room that's at 100 degrees Celsius, starting at 100 degrees Celsius. What happens is we know that from experience that the tea is going to cool down over time by the fact that the cup is not fully insulated and we have some energy out or some heat out. Heat is denoted by Q, and the heat is going to heat up the surroundings slightly. And so our energy inside our control volume now is going to decrease because of that. So we're not going to decrease our mass, but we're going to decrease our energy inside the control volume. In the following video, we're going to be introducing the concept of pressure, as it is paramount to understand what pressure means, how we measure pressure, and how we use pressure within thermodynamics. As always, thank you so much for watching. If you found this video helpful, please give it a thumbs up and subscribe to my channel for more content like this. Don't forget to hit the notification bell to stay updated on my latest videos, and really your support helps me in creating engaging content. If you want to learn more about the topic or have suggestions for future videos, please leave a comment down below, and thanks again for watching.